So oxoacid. So generally nitrogen and phosphorus both can make a oxoacid. The simplest example of oxoacid for nitrogen containing is HNO2 and HNO3. HNO2 is a nitrous oxide and oxidation state of nitrogen is +3, whereas HNO3 is a nitric acid and the oxidation state of nitrogen is +5. So both are weak acid and pure liquid is unknown. So you can easily prepare HNO2 if you are doing reactions of HCl and NO2, so you can easily prepare. Okay, similarly, if you are like barium nitrate, then and you are doing reaction with sulfuric acids, you can make HNO2 nitric acid and nitrous acid and barium sulfate. So in cases that also HNO2 decompose and produce nitrogen oxide and nitrogen dioxide. And similarly, aqueous solutions of HNO2 also decompose and produce H3O plus ion or NO3 minus ion. And due to this, HNO2 act as a both oxidizing as well as reducing agent. So HNO2 has a +3 and +5 oxidation state, so that's why it can act as a in HNO3 the oxidation state is +3 and the oxidation of nitrogen is maximum is +5 and it can go up to +1 also, so that's why it can act as a both oxidations and reducing agent. So the oxidation state can decrease as well as increasing, and therefore HNO2 is oxidizing as well as reducing agent. And it oxidizes Fe+2 and converted into Fe+3, so this is a removal of one electron. And similarly, iodine -2 iodine, tin +2 2 +4. So these are some other examples. So as well as for reducing agent like from NO2 minus to NO3 or MnO4 in MnO4 minus. The oxidation state of manganese is +7, which is converted into +2. So and this happens in presence of HNO2. That's why it can act as a reducing agent. The nitrates are very toxic and it's very harmful. So generally, it can easily bind and during cooking this NO2 minus react with protein to form carcinogen nitrosamine, and nitrite inhibit the growth of Clostridium botulinum, and which may cause food poisoning, and thus nitrite is a toxic substance. Then the structure of NO2 minus, which is similar to like CO2, and the angle is NON is like 115 degrees centigrade, and the distance between nitrogen and oxygen is 1.1 angstrom. And the nitric acids, the structure is like HNO3 and the oxidation state is +5. And this is the monoprotic acid, means it will release one hydrogen, and this is a like colorless compound, and this is acidic and little bit viscous when it is in concentrated. So the oxidizing agent and oxidizing power increases with concentration, and solution concentration looks like a yellowish. And why? Because during the decomposition it produces NO2 ion, and the color of this nitrogen dioxide gas is brown color. Okay, so generally that you know that there is always confusion between NO2 minus and Br minus in your quantitative analysis. And the acids can be easily prepared by heating metal nitride with concentrated sulfuric acid. So this is a metal nitrate and sulfuric acid, so you can heat it will produce like sodium sulfate, and HNO3 vapor, and if we'll decrease the temperature, again we'll get in liquid form. So you can prepare by Brightland ion process and Oswald process. So this is the method like nitrogen and oxygen in electrical spark, it will produce like NO, and if you are doing oxidations, it will produce like nitrogen dioxide, and again if you are doing oxidations, you will get HNO3. Similar for Oswald process, you need HNO3, you need ammonia. From ammonia you can easily prepare. So initially this ammonia will react with oxygen in presence of platinum catalyst and produce nitrogen oxide, and for this nitrogen oxide you can do more reactions with oxygen and produce nitrogen dioxide, and then like hydrolysis you will get HNO3. So NO is recycled in oxidation chamber, and the process produces 60% HNO3 by weight percentage, and the further distillations gives up to 68% acid. So dehydrating from HNO3 to with concentrated H2SO4 and mixing with acid, 72% this solutions followed with distillations. So it can react with non-metal as well as metal. So mostly dilute HNO3 are non-reactive with non-metals, and even the concentration of HNO3 has no actions on nitrogen, oxygen, chlorine, and bromine. Even the concentration of HNO3, if you then react with boron, carbon, phosphorus, sulfur, iodine, etc., and the reactions are below, like if I have like HNO3, so if I am reactions with boron, so I can produce like H3BO3, and for carbons, carbon dioxide, for phosphorus, H3BO4, for sulfur, sulfuric acid, and for if I have iodine, then HiO3. So the general reaction is you can write like this: from HNO3 like nitrogen pentoxide and water molecule, from nitrogen pentoxide, nitrogen dioxide and oxygen, and this oxygen react with this carbon and produce the carbon dioxide. So like this, and this is the overall reactions. So you have to cut like nitrogen pentoxide and etc. Similar for like first two steps are common, and if you are taking here sulfur and oxygen, it will produce sulfur trioxide, and then you have to do hydrolysis, so you will get a sulfuric acid. So the reaction depends on the concentration of HNO3, temperature, and nature of the metal. So generally even gold does not react with the HNO3. So mostly noble metals they don't react with HNO3. So HNO3, if copper and silver metal can react with dilute HNO3, it will produce nitrous oxide, whereas with the concentrated HNO3, it will produce nitrogen dioxide. Then some of the metals are reactives. So it depends upon the concentration of HNO3. Either it may produce N2O or NO. So with very dilute HNO3, hydrogen can easily form with magnesium and manganese like metal, and even if you have some kind of alloy, and if you are doing reaction with NaOH, you can produce like nascent hydrogen, and this nascent hydrogen, if you can react with nitric acids, you will get ammonia and water as a product. So, but mostly all the metals can dissolve in aqua regia, and aqua regia is nothing but it is a composition of HCl and HNO3 in 3-1. So you have to take HCl as 3 part and 1 part of HNO3. So the mixture is known as aqua regia, and this is a very powerful oxidizing agent. and dissolves all the metals, including those and gold and platinum, which are not dissolved in your simple individual acids. So the two acids on mix reacts. So the process is very simple. Why these metals are dissolved? Okay. So when you mix the HCl and HNO3, it converted into NOCl, this Cl and water. So this NOCl and Cl make aqua regia more powerful oxidizing agent. So what will happen when you dissolve this gold into your aqua regia solution? This gold will react with chlorine and produce gold trichloride, and again this trichloride will react with one chlorine ions and produce gold tetrachloride. Okay, similar with platinum also. So okay, so in a high concentration of chlorine ion, it's further stabilized, and okay, so that's why this is the reason they are converted into some ions, and hence it is highly it is soluble in aqua regia. So oxoacid for phosphorus. So like for similar phosphorus, you can make a different kind of acid, like hypophosphorus acid or phosphoric acid or metaphosphoric acid, orthophosphoric acid, pyrophosphoric acid, and all have different oxidation states. So for hypophosphorus acid, it's very easy. So you have to just heat phosphorus with barium hydroxide, and you have to treat this reaction mixture with dilute sulfuric acid. So you will get H3PO2 hypophosphorus acid, and the solution crystallized to H3PO2, and it is a reducing agent due to the pH bond. The structure is like tetrahedral structure, and one phosphorus is attached with like OH, and one oxygen atom is make a double bond with phosphorus. So due to this one OH minus, this OH molecule, it can act as a monoprotic. Okay. Then H3PO3, and this is a diprotic acid. Okay, so there is a slightly difference between H3PO2 and H3PO3 structure. So here in H3PO3 there are two OH molecules. Okay, and the third hydrogen is directly linked with phosphorus, and one oxygen is attached with directly phosphorus to double bond. Okay, so by dissolving P4O6 in water, you can produce H3PO3. Even you can produce with phosphorus trichloride. If you are doing reactions with water, you can get H3PO3. Then the solutions of crystallization give white crystal of this H3PO3. And if you are doing these proponations and you will get H3PO4. Okay, and it is also a reducing agent due to the pH bond. So it can reduce this AgNO3 into Ag metal. Okay, so similarly, for if you can do reactions with mercury chlorides, H3PO3 is also converted into H3PO4, and as I told you, the structure is it is a diprotic. So here two OH groups are attached with phosphorus, and when you dissolve this H3PO3 into water, this 2H plus will release, and hence it can act as a diprotic acid. So phosphoric acids are like H3PO4 is known as orthophosphoric acid. H3PO3 thrice H3PO3 raised to n like polymerizations, it is known as metaphosphoric acid and pyrophosphoric acid like H4P2O7. It is known as pyrophosphoric acid. So this all can be obtained by, you can prepare by the control hydrations of P4O10. So like from P4O10, if you can remove small amount of water, you can make meta acid. Similarly, from this you can prepare a pyro acid, and if you have excess water, then H3PO3, which is known as orthophosphoric acid. So you have to just add water. Okay. So from P4O10, if you are adding water, so you will get this. This is a product, and this is the reversible process. So if you are doing dehydrations, so you will get a reverse. Okay, so this is the reverse. So the pure H3PO4 is manufactured by furnace process, and molten phosphorus burnt in furnace with air and steam, which produce H3PO4. So for phosphorus, if you can heat with oxygen, you can produce this P4O10 that we have already seen. And if you are dissolving this P4O10 into water, you will get H3PO3. Okay. And in this structure, like 3 OH and 1 phosphorus is directly attached with double bond. Oh, so the structure is tetrahedral, but here there are 3 OH. So that's why it is a triprotic acid. So it can release 3 hydrogen. Tri-basic acid. So it can release 3 hydrogen. And if I'm talking about acidity or basicity of this H3PO3, that we will see later. I thought maybe it is here somewhere, but that we will see later. So this is the dissociation constant. Third dissociation constant is a very less compared to first dissociation constant. You can prepare a different kind of sodium salt of this H3PO4 also. So for like primary, secondary or tertiary phosphates. And if you're, this is a H3PO3 as an acid, and if you are doing reaction with NaOH, so it is a like neutralization and makes this kind of salt. Okay, so this is a primary salt, and if you are doing, if you are heating this, so removal of water molecule and it produces metaphosphate. Similarly, if you are heating secondary salts, you will get pyrophosphate, but with tertiary it will not produce any kind of salt because there is no hydrogen atom in your sodium phosphate. So for dehydration of primary, secondary, you will get some kind of salts. With tertiary, it's not possible. H3PO3 is a highly viscous solutions because it can make a 3 hydrogen bond with water. And metaphosphoric acid is a polymeric, so like this kind of polymerizations is there. So linear and cyclic polymeric structure are found. The most common cyclic ones are cyclotrimetaphosphate, and the structure is like P3O9 3- and cyclotetrametaphosphate like P4O12 4-. So there are 2 types of PO bonds, ring and terminal, and the terminal oxygen atom are equivalent due to the resonance. So if I am talking about the acidic strength, if I am comparing these 3, H3PO2, H3PO3 twice, and H3PO4. Okay, so which one is stronger acid? So in all these 3 acids, 1 oxygen atom is attached with phosphorus via double bond. Okay, and this contains 1 OH minus, this contains 2 OH minus, and this contains 3 OH minus. Okay, so that's why we have to consider these things here. So from formations of conjugate base, you can get the idea which one is a stronger base. So conjugate base, for this you have to remove 1 H here you have to remove 2H because 2OH is present, and here you can remove 3H because 3OH is present. So like -1/2. So the negative charge per oxygen atom. So we have removed one hydrogen, so that's why here the negative charge is 1, and we have left 2 oxygen atoms, so -1/2, the value is 0.5. Similar here, we have removed 2 hydrogen, so the charge on oxygen is -2, and we have a 3 oxygen atom. Similarly for here, and the value is like 0.5, 0.63, and 0.75. Okay, so this value is lower here, so that's why this is a stronger acid, and this is a little bit weak acid. So when negative charge per oxygen atom is high, the anion has a larger attractions for H plus ion. So this has a larger attractions for H plus ion, so it cannot remove the H plus easily. Okay, and the acid ionized less and weak as and vice versa. Okay, so this is a highly attraction for H plus ion, so it will not easily release. So that's why this is a weak acid. So H3PO4 is a weak acid compared to H3PO2. So it can make easily halides for like MX3 and MX5. Okay, so nitrogen can easily make a NX3 type of halide, but NX5 is not possible for nitrogen because it does not contain the vacant d orbital. Rather, for phosphorus, antimony, and arsenic, there is a d vacant orbital is there, so they can easily form NX5 kind components. Okay. So these are the properties for halides. The stability is increases like this. Same ionic number of bond is always increases like this. Melting point, boiling point is always increases like this, and even hydrolysis tendency is little bit decreases. So due to this metal character, they are not easily hydrolyzed. Then for trihalides, like NF3, NCl3, and Br3, and I3. So these are the gas. This is in liquids. The structure is tetrahedral. This is a stable. This is a explosive nature. So unaffected by water, and this is a readily hydrolyzed. So suppose same if you have a trihalides, then and if you are comparing about this structure, so these are the physical state. Like this is a gas, liquid, solid, and all have a like pyramidal structure. The stability is decreases with increasing the atomic number of halogen. Bond angle also increases, and all are hydrolyzed by water rapidly. So NCl3 and PCl3 is completely hydrolyzed by water, whereas arsenic trichloride is similar like NCl3 and PCl3 also, whereas antimony and bismuth chloride are partially ionized, hydrolyzed by water. So these are from NCl3 you can produce ammonia, from PCl3 you can produce H3PO3, and for arsenic you can make H3AsO3. Whereas tin and bismuth chlorides are also hydrolyzed to oxysalt. So NCl3 hydrolyze, and it can act as a base, whereas PCl3 during hydrolysis to hydrolyze to produce acid. So the difference is for NCl3 there is a nitrogen as a lone pair of electron, so it has a tendency to give electron to water molecule, whereas for PCl3 there is a vacant 3d orbital is there, so that's why they are accepting the electron, so that's why they can act as a acid. Then pentahalides. So pentahalides of phosphorus are you can denote by px5. So the px5 is produced because of the vacant d orbital, And if I am talking about the physical state, so these are the gas and these are the solid. And structure is this a trigonal bipyramidal structure, and the stability is decreases with increasing atomic number of hydrogen, and hydrolysis character is increases. So the structure of trigonal bipyramidal is like that. Okay. And the PFI is tetragonal bipyramidal is a gas, liquid, and solid state. However, PCl5 is a gas, liquid in trigonal bipyramidal, but it crystallized to form this kind of complexes, PTCl4 and Cl6. So it is changed to PCl5 is a Cl minus ion donor, as well as a Cl minus ion can act as a acceptor. So these are both are the this is a tetrahedral structure. It contains 6 chlorine atoms, so that's why it is a octahedral. And PCl5 is widely used to prepare the chloroderivatives. So generally it is used as a chlorinating agent that we have already seen in organic chemistry, or like thionyl chloride or phosphorus oxychloride you can use as a chlorinating agent. So mostly it is used for like carboxylic and hydroxyl group. So like if you are carboxylic and doing reaction with PCl5, so you will get like chloride. Similarly, if you have like hydroxide, so you will get alkyl chloride, say acyl chloride. So you can also replace OH with sulfuric acid. Like if you have phosphorus pentachloride and H2SO4, so you will get a chlorosulfuric acid, and you can replace this another hydrogen with PCl5, you will get sulfuryl chloride. So PCl3 and PCl5 both react with P4O10 to produce a phosphorus chloride. So its method is very simple. And PCl5 is hydrolyzed by water and produce like H3PO4 phosphoric acid. For isolations of nitrogen and phosphorus is very easy. Nitrogen is occur in atmosphere around 78%, and it also found in nitrites and NH4 compounds and organic compounds. So you can easily prepare N2 in laboratory when you will reaction between like ammonium chloride and sodium nitrite. So like if you are heating, so you will get a sodium nitrate, and further you are heating this with ammonium chloride, you will get nitrogen, sodium chloride, and water. So ammonium nitrate is an explosive, so it is not heated alone. So you can even obtain pure nitrogen when you are heating sodium azide. Then ammonium dichromate, if you are heating it, you will get a nitrogen. Then even you can manufacture nitrogen on large scale. So it is prepared in large scale by liquidifications and fractional distillation of liquid air, because nitrogen and oxygens are differ in their boiling point. So the boiling point of nitrogen is minus 196 degrees centigrade and oxygen is 1983 degrees centigrade. So this is a free air which contains carbon dioxide, so you have to liquidify liquid air and then you have to go for a fraction distillation, so you will get a nitrogen. And isolations of phosphorus, so phosphorus occurs mainly in the form of like phosphorus phosphorides like Ca3PO4 twice, fluorapite, fluoroapatite, and chlorapatite. So these are the main sources. So for phosphorus is obtained by the reductions of phosphate rock with silicon dioxide and coke in electrical furnace. So you will get easily phosphorus. So white phosphorus is inflammable in air, and so you have to get it into the water. So this is the end of the chapter. So this is a reference book, so they are giving about a little bit information about the fertilizer. So mostly, as you know, that this NPK is the most vital fertilizer, which is essential for the crop. And if you want to read, then you can read which kind of fertilizers, how they can prepare, and how they can use by plants also. Okay.